Alright, welcome back to Discrete Structure, CSE 215, Lecture 4B. So this will be mostly a review for things that you've already encountered in other courses. One is the idea of summations, and we touched on this really briefly. I mentioned it when we were talking about unions and intersections of numbers of sets. If we have some sequence of terms, for example, A5 plus A6 plus A7 plus A8 plus A9, we can write this in a shorthand notation as saying the sum from I equals 5 to 9 of A sub I. And this just means write down this term, whatever this is. It could be a simple AI, or it could be a big, long, complex expression. It could even be another summation or a function. But set I equal to 5 and evaluate this expression. Then set I equal to 6, evaluate this expression, and so on all the way up to I equals 9, and then add up each of those expressions that you evaluated. So this is basically a for loop in a programming language. For I equals 5 to 9, and we've got a running sum where we keep adding whatever this expression is with that current value of I. So this maps directly into one of the key constructs of a programming language, a for loop. So one thing to know is that this index I is arbitrary, right? This would be exactly the same thing as the sum from W equals 5 to 9 of A sub W, right? It's just a placeholder, and it's just like in a for loop. If we have a for loop for I equals 5 to 9, and everywhere that we use I in that loop, we replace it with a W, and we say for W equals 5 to 9, the end result of that loop is going to be exactly the same. Right? And we shouldn't be using that value of I or W outside of the loop. Sometimes we do, but we shouldn't. So the index is basically arbitrary. This is called the index of summation, and the choice of it is really up to us. There's properties of this that probably won't be very startling. So for example, let's just say the sum from I equals 1 to n of A times x sub I. So A times x1 plus A times x2 plus A times x3 all the way up to A times xn is the same as A multiplied by the sum from I equals 1 to n of xi. So we can pull constants out as long as this term A is just a constant, a number. It doesn't involve an A inside it. And similarly, sum from I equals 1 to n of two things that do involve I, xi and yi, we can split that into two summations as follows. So it's this thing plus this thing. And if you do this in pieces, if you think about what this means for a particular value of n, you can convince yourself that this really is equal to this. It's a trickier question to show this in general. We can show it for specific examples, and we'll do that in class at the board. But to show that this is true for any expressions xi, yi, and any n, that's harder. That takes something called mathematical induction. It's going to be one of the main focuses of this course. We'll get to it in a few weeks. And we'll come back to this and see this as an example of what we can use mathematical induction for. Okay, another thing to keep in mind about this index of summation is that we can move it around. So let's go back to our example, A5 plus A6 plus A7 plus A8 plus A9. And these are just numbers, right? So this is the sum from I equals 5 to 9 of A sub I. Well, maybe we don't like going from 5 to 9. Maybe we like going from 1 to something. So we could do the following. We could go the sum from I equals 1. And instead of adding AI, we could add A sub I plus 4. And here we could run I from 1 to 5. Well, remember, what does this expression mean, this summation? It means set I equal to 1 and evaluate this. Well, what's I of 1 plus 4? 1 plus 4 is 5. So this is A of 5. And then if I equals 2, 2 plus 4 is 6. So this is A6. If I is 3, 3 plus 4 is 7. This is A7. I is 4. This is A8. and the last value of I5, this is A sub 9, and the summation says add these all together. Well, that's exactly the same as this. So this summation is exactly the same as this summation, but in this case we changed the index to go from 1 to 5. And we did that by changing what this expression was that we were summing. And sometimes it's useful to have summations that start from 1 instead of some crazy value like 5. So we can change the index. So we'll play with this, and we'll see ways to take some certain summations, such as a geometric series, and come up with expressions to describe what those are equal to. One final comment, we can do double summations, for example. Sum from I equals 1 to 5 of the sum from j equals 1 to 3 of I times j. And don't be tripped up by this, right? Just think of this as an expression that you're summing. So what does the summation mean? It means set I equal to 1 and write down this expression. Well, what's this expression if I equals 1? It's the sum from j equals 1 to 3 of 1 times j. Okay, what if I is equal to 2? What is this expression equal to? It's the sum from j equals 1 to 3 of 2 times j. And if I equals 3, this summation is the sum from j equals 1 to 3 of 3 times j. And if I is 4, it's the sum from j equals 1 to 3 of 4j. And if I is equal to 5, it's the sum from j equals 1 to 3 of 5j. And since it's a summation, add them up. So this whole expression is the same thing as this expression. And how do you find what the value of this is? Well, figure out what each of these individual summations is, substitute them in, and then do your big addition. Okay, so we'll have an opportunity to do this on the board as well. One final note about summations, we can also do things like sum from I equals 1 to infinity, or even sum from negative infinity to positive infinity. And we have to be careful what we sum in this way to make sure it makes sense, because if we add an infinite number of things, usually it tends to blow up, but not always. Sometimes this will actually lead us to some number that's not just arbitrarily big. Okay, so the last thing I want to mention in this unit is matrices. And we touch on matrices in CS 120, Intro to Engineering. We play with MATLAB. We use matrices to solve simultaneous equations. I'm going to talk very, very briefly about the ideas of matrices. So a matrix is basically a rectangular array of numbers. So for example, 1, 2, 3, 4, negative 6, 0, 5, 14, and 2.6. That's a matrix. Okay, these are columns and these are rows, and we can refer to elements of this as A sub ij, where I is the row and j is the column. So sometimes we'll write this matrix as simply the set of elements ij, and sometimes we use square brackets to make sure we're not confused with other mathematical objects. So this is a two-dimensional matrix. It's got 3 rows, it's got 3 columns, so it's a 3 by 3 matrix. And we can generally add and subtract matrices as long as they have the same dimensions. And how do we do this? We just do it element by element. So let's look at some 2 by 2 matrices. So here's a 2 by 2 matrix. And here's a 4, negative 4, 2, and 0. Here's another 2 by 2 matrix. And if we want to add these, we do it element by element. 1 plus 4 is 5. 2 plus minus 4 is negative 2. 3 plus 2 is 5. 4 plus 0 is 4. Very straightforward. We can subtract in the same way. We just subtract term by term, and that gives us the difference of 2 matrices. And we can multiply a matrix by a number by just multiplying each term by that number. So this would give us the matrix 5, 10, 15, 20. But it's a trickier business to multiply 2 matrices together. to multiply these matrices, we don't just multiply term by term. We could, but it's not a very useful operation. It's much more useful if we do something which, again, we touched on in CS 120. We take the first row and the first column and we do what's called a dot product. So 1, 2, dot, 7, 2, and it means multiply the first terms, multiply the second terms, and then add them. So this dotted with this would be 1 times 7 plus 2 times 2. That's 7 plus 4 is 11. So the upper left element of this product would be 11. To find the element in row 1, column 2, we take row 1 of this matrix, column 2 of this matrix, and we dot them together. 1, 2 dotted with 8, 0. So 1 times 8 is 8, 2 times 0 is 0. This is just 8, that's the element up here. Now we don't really need to do this for this course, okay? I mention this because this is a logical place to talk about it because it ties in with sets and stuff. But we're not really going to need to do this, and if we need to multiply matrices, we usually have a calculator or a computer program to do that for us. But I want to mention something interesting about this. If A and B are matrices, A times B is generally not equal to B times A. So matrix multiplication is usually not commutative, and that's interesting because pretty much all our multiplications up to this point have been commutative. And here's a genuine operation that is generally not commutative. In fact, in a lot of cases, this may not even be defined because there's specific requirements on the dimensions of these matrices to allow us to do this multiplication. Okay, there's also a particular matrix called the identity matrix, and the identity matrix basically has 1s on the diagonals and 0s everywhere else. So for a 3 by 3 matrix, this would be the identity matrix. And the identity matrix is cool because if we multiply it by another matrix A, we just get back A. And in this case, our multiplication will be commutative. But this only works if A is actually a 3 by 3 matrix as well. All right, so the last piece of this is if we know that that we have a matrix A and we have an identity matrix, we can ask the following question: is there a matrix B such that A times B is equal to the identity? And it turns out in a lot of cases there is no such matrix B, but if there is, then we can write that B is equal to the inverse of A. And this is kind of like a reciprocal. It's saying that if we take this inverse and we multiply by A, we get something like 1. The identity matrix is basically like a 1 for real numbers because it doesn't change the value of a matrix A when you multiply it. So in some cases we have an inverse. And understanding this and how to work with this, and in particular being able to calculate the inverse of a matrix, this is one of the things that drives our society right now. This is used in so many branches of science. It's used in chemistry. It's used in finance. If you can invert matrices efficiently, you can do things like solve systems of equations simultaneously. We do this in 120 when we do KVL, KCL. But if you have 10,000 equations in 10,000 variables and you want to find a solution for all of those equations simultaneously, if you can invert a 10,000 by 10,000 matrix efficiently, you can solve those equations. And it turns out, for example, if you have a portfolio of stocks in the stock market and you want to find a way to buy and sell certain stocks to optimize that portfolio, it comes down to solving systems of equations, which means it comes down to being able to calculate inverses of matrices. And this is why Wall Street consumes supercomputers and uses things like neural networks and artificial intelligence, because those things can do problem solving when it's not practical to actually go about trying to find an inverse of a matrix, because this is an expensive operation, especially if your matrix is something like 1,000,000 rows and 1,000,000 columns. So this gets into an area called linear algebra. And you're all computer science majors, presumably, so you'll take a course called Math 215. That's linear algebra. And this is one reason that linear algebra is part of the computer science curriculum, is because this is really key to being able to solve equations and do all kinds of useful manipulations. All right, so in the homework we'll talk about 0-1 matrices, which will bring us back to Boolean algebra and tying that into set theory. But that pretty much completes our discussion of sets, functions, summations, sequences, matrices, and all of this first unit material. So next unit we're going to start talking about propositional logic, propositional calculus. And this is going to take us into the idea of doing proofs, which is going to be another one of the central pillars of this course. So we'll start on that next time.